In this video, we will work through a few examples using right triangle trigonometry, some using special angles, values that you should know, and maybe some others that where we're going to use the calculator. So our first one is an applied problem. A surveyor at a point A on the ground, 25 feet from a flagpole, looks at the top of the pole using a 30-degree angle. Use trigonometry to determine the height of the flagpole. So we have some scenario here where we have some person and they're a surveyor, and we've got a flagpole, and we got a flag on it. And we have, from the situation, we can build a right triangle. Now, in this particular case, we are going to happen to ignore the height of the surveyor just for this first example. Using a 30-degree angle here to look at the top of the flagpole and the fact that the surveyor is 25 feet away, and we want to know the height of the flagpole, and I'll call that h. Now, this problem is solvable by using your special 30, 60, 90 triangles, but we're looking to start to use trigonometry to help us solve some of these problems. And it's more about the procedure, not about these particular numbers. So in this particular case, what I do is I think about the information that I have and the problem I'm trying to solve. In this particular case, I have this angle of 30 degrees, and I have that 30-degree angle there. I have this 25 feet. Now, I would consider 25 feet to be the side that is adjacent to 30 feet. Oops, jumped on me there. And then I have what I'm looking for, the height of the flagpole h is going to be the side opposite. So when I think about some particular angle theta, and the fact that I have the adjacent side, I'm looking for the opposite side, it makes me think of the tangent function. So I could say that tangent of 30 degrees is equal to the length of the opposite side, h, times the length of the adjacent side. So I can create a trigonometric equation here. Little bit of algebra, I'll multiply both sides by 25. I get 25 times tangent of 30 degrees equals h. Now, in this particular case, 30 degrees is one of our special angles, so I don't necessarily need to use my calculator. I can say 25 times root 3 over 3 is going to give me the height of my, the height of my flagpole. And if I want to give the exact value, it would be 25 root 3 over 3 feet. And that's an exact value. But generally, the approximate value would be fine. And it wouldn't be a terrible thing at this point to put it into the calculator and have 25 root 3 divided by 3. You get about approximately 14.4 feet. So there's one example of using trigonometry to solve a triangle. A second example, more of using just a triangle, not necessarily a situation. What you'll notice in this particular case, the given angle, however, the given angle of 56 degrees, 56 degrees is not an angle that we would know anything about. We can't build its trigonometric value off of our 30, 60, 90 triangle or our 45, 45, 90 triangle. So we are going to have to use our calculators and approximate values here. Now I'm going to use kind of some standard notation to label the rest of these. I'm going to call this angle 56. I'm going to call that alpha. Therefore, the side opposite would be considered to be A, leaving this angle to be beta and this side B. And obviously, this would kind of be a gamma there, and we'll call that C. And my task becomes to find, let's just highlight them here. My task, find the value of B, find the value of A, find the value of beta. Beta is probably the easiest one in this particular case to find. That beta would be 180 degrees minus the 90 degrees from the angle we know, and minus 56 degrees from there. And it's just going to be really 90 minus 56. And so that's going to be 34 degrees. So I've got my B. Not so bad. From here, I have to find A and B. Traditionally, we'd use the Pythagorean theorem, but I don't have enough sides. And there's options here. It doesn't really matter whether I find A first or I find B first or whether I use alpha or beta. You just have to create a right triangle trig equation like I did in the last example. So let's say I want to find B first. So I want to find B. I would look at my angle alpha, or I could use my beta, but let's say I use alpha and B. For alpha, 56 degree, B is the adjacent side, and C is the hypotenuse. That makes me think of the cosine function. Cosine of 56 degrees, defined as the length of the adjacent side over the length of the hypotenuse. So I've created my trigonometric equation. Multiply both sides by 15 to get my B. And it's just a calculator exercise. We don't know anything about 56 degrees. Make sure your calculators are in degree mode. And I'll have 15 times the cosine of 56 degrees. And you get approximately, and maybe I should erase the equal sign and use an approximately symbol there, approximately 8.39. And I don't have a unit, so it's just 8.39. Now here's where I would encourage a little bit of due diligence with these trigonometric problems. Now that I have two sides, I could use my side length C and my side length B to calculate the side length A. The only reason to avoid that would be because my side B is a rounded value. If I use a rounded value to perform another calculation, I'll be a little farther off. So in this case, I'm going to try to use exact values whenever possible. What I could do is, to find A, I know that 56 degrees is an exact given value, and I also know that the 15 here is an exact given value. So I could use that. The side A is opposite of 56. C is my hypotenuse. I write another trig function. Let me grab another color here. Sine of 56 degrees equals opposite over hypotenuse. And I perform very similar algebra to what I did before to get my value of A. And this is just, you retain some accuracy. People, in the science fields talk about percent error and sig figs and things like that. And that's just what we're trying to maintain a little bit here. And I get 12.44. We'll go to the hundredth there. I didn't specify decimal places in this particular case, but this is where we might go with that. So if I take a look at the full problem here, it took me 3 steps to find the missing angle and then 2 trig equations to find the missing sides. And that's what we get there. We're going to do one last example. The first one was an applied problem. The second was to solve a triangle given a diagram. And the third here is going to be solve the given triangle, and I don't have a diagram. So I need to create my own diagram. In this particular case, I still see my gamma being 90 degrees. We're still using right triangle trigonometry to solve these problems. So draw some right triangle. That'll be my gamma of 90 degrees. Common notation is that side C is going to be opposite my gamma. So that means I put my 33 right here. And my beta of 37 degrees, it doesn't really matter whether I put it in this angle or over here in this angle. It doesn't really matter. I just have to choose one. I'm going to choose to put it here. But once I've made those choices, a lot of other things fall into place. That the side B has to be across from beta. That makes this the angle alpha, and this the side A. And those are the 3 values I need to find. I would probably find alpha first in the same way that I found in the previous problem, 180 degrees minus 90 degrees minus 37 degrees is going to give me an alpha that is equal to 53 degrees. I have an alpha of 53 degrees. And now I have to find my side B and my side A, like I did in the previous problem, by writing trig equations. I would encourage you at this point to pause the video, try to find A and B on your own, and then come back and work through the solutions. see me work through the solutions, that is. So if you did that in your back, remember that I might not choose the same trig functions as you because there's a variety of ways of doing it. You just want to be concerned that you got the right lengths of sides. All right. So I'm going to use beta to find A first. A is the side adjacent to beta, so I'm thinking cosine. Cosine of 37 degrees is equal to the adjacent side over the hypotenuse. That will become A equals 33 cosine of 37 degrees. Now 37 degrees, not a special angle. I'm going to use my calculator, and I just type it in, 33 cosine of 37. If you're having trouble with that and you're thinking you're having some issues, make sure your calculator is in degree mode and not radian mode, and we'll get 26.4. Now we do have a label here, so I'm going to call that inches. So A is about 26.4 inches. And then I have one last solution to get. Kind of have sine of 37 degrees equals B over 33. B is the side opposite, and the sine function is defined as opposite over hypotenuse. Quick bit of algebra, 33 sine of 37 degrees equals B. B is approximately, so that's 33 sine 37 degrees, well, I put it in the calculator, 19.9 inches. So hopefully you got those, even if you might have used cosine or sine differently and your alphas and betas differently than I did. Just a quick 3 examples on solving triangles completely using right triangle trigonometry. Thanks for watching.